Welcome to the another session in Frontiers in CFD. So today we will see the phase change material for thermal management of lithium-ion battery pack. So we are considering a single cell, and accordingly we'll see how the phase change material takes the heat from the cell. So the objective of today's session is preparation of geometry of lithium-ion battery pack with the phase change material, generate mesh, name selection on computational domain, applying the boundary conditions and visualizing the results. Welcome you all. Today we will see the simulation of lithium-ion battery which uses the phase change material. So we'll use the ANSYS design modeler for preparation of geometry. So we'll be using this for a single cell. So the analysis which is done for single cell can be implemented for n number of cells. So let's start with the fluid flow fluent option. Let's open the geometry over here. So new design modeler geometry. So create, first of all set the units. I will set it to mm. So click on any one of the plane. So create primitive, then cylinder. Take the z component to be equal to 0, y component to be equal to 65. Make this is equal to 0. Radius will make it 17, and instead of add material I will make it add to frozen. So this is the first cylinder which has been generated. Another cylinder we will generate. So go to the create primitive. So one more time we are considering the cylinder. So y component I will put as 65, z component I will make it 0, whereas the radius I will make it 9, so that it will be 18 mm. Instead of add material I will make it slice material. So let's generate. So now we have generated the geometry where we have the two things. One, it is the your PCM, and second one it is your lithium ion. So one by one we'll denote this as a name over here. So this is your PCM, so we'll call this as, rename this as a PCM, and second one we have it is a cell. So let's denote this as cell. So these are the first part which we are done. Now let's go back to your workbench window, open the mesh, click on the edit. So the geometry has opened in the mesh. So let's observe this. First one it is PCM, second one it is your cell. Now we have the mesh. So let's generate the default mesh first, and then we'll see how much modification it is required for comparatively a better quality of mesh. So depending on how much is the time required, accordingly also we can proceed. So let's make it the different element size. Let's say 0.00, let us say 1, and let's make it generate and just see how the mesh generates. So we want the mesh to be a comparatively better in size. So let's see the statistics over here. So it is around 10,09,746. So these are many number of nodes which we have. So based upon this we are going to proceed. So I took 0.001 over here as a element size. Now let's give the name selection on this geometry. So first of all I will hide the PCM. Click on this, select name selection, and let's denote this as a cell boundary. So let's have this as the cell boundary, make it okay. Then one more time, so show all bodies. Now go for your PCM. So I will hide the cell now. So hide body. So this is your PCM. So let's select all, then create name selection. So denote this as your PCM. So these are the two things which we are done. So make it show all bodies here. So mesh we have generated over here. So this is the first. Then we have done the name selection, cell boundary and PCM. So let's make it update. Once you have updated, you will see the message, the mesh translation to Fluent was successful. So once this is done, you can actually close your meshing. Now next is to open the setup window. So go to the setup window, click on edit, depending on the number of processors you have. So I click it 14, make it start. So wait the time till that is loaded. So once geometry is loaded, go to the transient, select the gravity, let's put it minus 9.81. Click on the style option, so this will be information available. Go to the model option, energy equation, I will turn it on, make it okay. Then in case of viscous, I go to the K epsilon, enhance wall treatment, then thermal effect and curvature correction. So this is the option I am selecting. Next thing is solidification and melting. As we are using the PCM, so PCM will go on to melt. So let's go to the material. So instead of air now, I will define one new material over here. Say N octa decane. So this is the material I am specifying, NOCT. Okay. So I just write this formula. So first of all, putting the value of density over here. So that is equal to 721 kg per meter cube. Then specific heat 2180 I will enter. Then thermal conductivity I will put it 0.15. Then this viscosity 0.035 available here. Next is your the pure solvent melting heat. I will put this value as 1900. Solidus temperature I will put it as 303 Kelvin, and the last temperature I will put at 305 Kelvin. So this is 305 Kelvin. So make it change create, make it okay, then close. So we are done with the N-octadecane. Now it's time to specify the solid materials. Where are you going to use the solid as a nickel? So that we need to add. So make it copy and then close, then close. So we have nickel and we have the aluminum which has been added. So go to the cell zone condition over here. So in case of cell, ensure that this is your solid. So while using the solid, ensure that this is nickel, then close. Then PCM, it's a fluid here. So an octadecane that we have just specified in the fluid zone. So now this is about the cell zone condition. Let's make it a boundary condition. So cell boundary contact region, I will go with the edit option available. Once you click on the edit, click on the temperature. So I put it some value which is around 307 Kelvin. Change the material to nickel, make it apply and close. So make it apply here again. Go to the wall cell, click on this edit option available. So one more time you need to put the same boundary condition, let us say 307 Kelvin, make it nickel, make it apply and then close. So this is how the boundary condition that we have specified. Then go with the reference values. We don't need to change anything over here. Then go to the report definition. So in first case I will go with the area weighted average. So in area weighted average, I will go with the solidification and melting. So liquid fraction, where I want to visualize, at a PCM. So make it okay and then close. One more time, I need to go with area weighted average. Now I will get with the temperature. So instead of static temperature, I will put it total temperature and it will be at all. Print to console and create output parameters. Make it okay and then close. So once this is done, click on the initialize over here. Once you click on initialize here, animation options will be available. So go to the calculation activities. Now in case of calculation activities, go to the solution animation. So click on new object, select contour. So what I want to visualize, solidification, melting, liquid fraction, select PCM. Color map option I will select as float so as to have a better scale, not the exponential one. Make it close, make it save display and then close. Select the contours. So this is your liquid solidification melting. So liquid fraction. So whatever the liquid volume fraction we have, so that is the one we are setting first. Then go to the solution animation again. I will go with the new object, then contours instead of solidification melting. Now let's take the temperature. So let's take the total temperature. So where I want to visualize, at all. So I need a scale which is better, that is float. Make it apply, then close, save display, close, select the contour to. Say the second is the total temperature. So I just put it total temperature animation, make it okay. So once this is done, go to the run calculation, click on calculation activities, make it auto save after 20, then go with the run calculations, put the number of time steps as equal to 100. Time step size I have taken as 1. You can take it smaller also in order to capture the minute details. So let's run it with the calculations. So let's see the process. So this is contours of liquid volume fraction which has been available. You can see it from 0 to point over there. So here you will see the variations in the we can say temperature along the PCM as well as the cell. Then here you will see the area weighted we can say average, that is for your total temperature, how the temperature variations are taking place, that which we can visualize. Another thing which is there is the contours of we can say the liquid fraction, how the liquid fraction is varying, so that visualization we can have. So the fraction is likely to go up because the heating has been taking place. So the solid which we have, it's will be subjected to the melting, and we can say the liquid fraction which has been visible over here. So we'll be having this chart which is going up, so that shows you the volume fraction which has been available. So similarly you can see the temperature, as the temperature rises your the melting is occurring, and that results in the increase in the value of temperature. So if you go with the other side, so that shows you the liquid volume fraction which has been available. So initially the liquid volume fraction which is near to the cell, so it will definitely go on to propagate along the we can say PCM. So this is how the temperature variation we have. So 302, now this is around 0.0140. So it is likely to increase once we go with a higher flow time. So right now we are just set to 100 as a number of time steps, and the time step size we are taken as a 1. So we'll have to run this for a long time in order to visualize how much the volume fraction we get on the left hand side. So right now it is around 0.016. It is yeah. So in this way we have to run it maybe around 500-600 seconds to visualize how the changes are taking place over the flow time. You can see the graph is going up for your liquid fraction. At the same time temperature reach around 303 over here. So this graph is likely to go up, you can see now further. So this is what the liquid fraction we have, this is how the total temperature we have. So we need to monitor this, how the liquid fraction varies over the flow time. So the right now the flow time is around 50 seconds, and you can see the liquid volume fraction is actually increasing. So we are at the end of the first 100 time steps. Uh, the liquid fraction has reached to around 0.027. So the temperature also has increased. So you can see the graph over here. Then variations can also be observed in terms of the cell and the PCM. Next thing is the liquid fraction which has been available. So at the end of 100 seconds, the calculation has completed. So you can see the graph, it is almost touching 0.03. This is around 303.25, and this is around the total temperature which is for your PCM and your cell, and this is the contours of liquid fraction. So this is how the things as of now at the end of 100 time steps. We definitely need to run it for more a number of time steps in order to visualize the things in better way. So let's run it maybe for further around. Okay, first save the work. Say cell with PCM. Okay, so cell with PCM, this is the name which we are following. So one more time, cell with PCM. So save the work. Okay, now let's one more time, let's run it for around 300 seconds and just see how the variations are there. So we'll run the simulation, and once it is completed, we'll check how the variations are temperature, variations of the liquid fraction, and how the color contours are being observed for total temperature as well as the liquid fraction. So around it is 96% is completed. So we have, you could see around 7,000, around 8,000 iterations have been performed. The flow time is around 400. So the liquid volume fraction is reached to around 0.35. Temperature is reached around 305. Sorry, more than 305.5. So this is how the contours of total temperature, how the temperature variations are there from the cell to the PCM, and here again how the liquid volume fraction is there for the PCM. So one, it will show you the fraction, and here it is the blue one. The blue one will show you the solid one, and the red one will show you the liquid one. So the calculation has completed. You can see the liquid fraction, then temperature, total temperature, PCM, and your the cell liquid volume fraction has been there. Let's run it further. If you see here, the flow time steps around 400. The flow time is around 400 seconds. So further we can run it. So right now it is just below 0.357 over here. So let's run it for one more 100 and check out what the things are changing. So the volume fraction has reached to around 4.457. Then this shows more than 305 contours of total temperature, and you can see the contours of liquid fraction. So we'll wait till the calculations are complete. So we have almost completed the next 100. So we'll be around 500 as a flow time. You can see how the variations are there. You can see the color contour, the color combination has changed over here. So that means the heat is coming through the PCM over here. So the liquid fraction has increased. It has reached more than 0.6 over here. Then if you see the temperature, it is again comparatively on the higher side, which is greater than 305. So this is the temperature variations. So this is your liquid fraction. So the color contour has changed. So this is your temperature. So we'll run it for further 100 seconds and we'll visualize how the things vary. So let's save the work first and run it again. So it has been around 585 as a flow time. You can see the variations in the liquid fraction. It is just slightly above 0.8. You can see the temperature slightly more than slightly below 306 here. Contours of total temperature you can see. Then the liquid fraction, you can see how the variations are been taking place in the PCM. So this is how the liquid fraction. So around 7 times 6 times steps are remaining. So at the end of 600 seconds, this is the situation for the liquid fraction which has been associated with the PCM. So calculation has completed. So if you see one more time, it's slightly above, slightly below 0.9, then around 306, and this is how the total temperature, and this is your liquid fraction.